Oh, Nickelodeon. Hello, this is Benjamin, and you're watching Disney Channel. All right, what's up, guys? Today we're gonna do problem 1591, strange printer number 2. Who would buy a strange printer? Nobody. What's the utility of this problem? I'm not sure, but it's a graph problem. It's fun. Comment if you're watching this because it showed up on the algorithm, or if it's just something you wanted to see someone solve. If this is a problem you solve and you want to see another solution, if you're totally lost, just tell me why you're watching it. For my 7 viewers out there, my 7 unique viewers, why do you watch it? Hit me in the comments and let me know so we can get through this together. You know what I mean? Also, I'm really excited this weekend because I got my own desk finally. We moved and I got my own desk. Right, guys? See, you don't need to be a FANG engineer at first. Just set yourself very small, attainable goals. And one of my goals was to have my own desk. And look at me, dude. You see me? I got a chair, a comfy chair. I'm not sitting on a stool. Look at that. You see that? Do you see that? Now watch this. I click this button. And now I can't go back. I pull it. Anyways, let's get right into this problem. Okay, so we got a strange printer. There's a strange printer with the following 2 special requirements. On each turn, the printer will print a solid rectangular pattern of a single color on the grid. This will cover up the existing colors in the rectangle. Okay, so if there's a grid and it's all blue, you can paint over it with green, and that would change the blue grid cells in the printed paper with blue, right? So if I had this paper and I was like, this rectangle is green, this is the green area, what I'm trying to say is, well, you could print over that with blue in any rectangular shape, right? Now it has to be a solid rectangular pattern, right? So I can't like print this, right? That was a bad decision for a shape. Let's just do that. What the hell? All right, a gun or something. You can't print a gun, right? It has to be a solid rectangular shape, okay? The same color cannot be used again, which makes sense, right? Because I could always print a gun if I wanted to do this, right? Like that, and then solid color. So you can only use a color once, and it has to be a rectangular shape, right? So it has to have some sort of rectangular look to it, right? Here's a few examples of rectangles. I did go to elementary school, right? These are all some rectangular examples. All right, so you're given an M by N matrix target grid where target grid row call is the color in the position row call of the grid. Okay, return true if it's possible to print the matrix target grid, otherwise return false, right? So given the constraints of this problem, is it possible to get the resulting target grid array, right? So for example, it would be impossible, just thinking about the problem example we just did, right? If we had this system and it was all green, right? If this area was all green, and then we were given a target grid where then it was blue like this, it would be impossible to get this, right? Because like you can only use a color once, so how would you get this gun shape? Right? You could get this, right? Because that would mean that someone printed green and then they printed blue over it. But would it be impossible to see this? Okay. I'm not trying to get all about the Second Amendment up in here, okay? That was just a shape you could draw. All right. Okay. So for this example, right, this is actually the resulting grid you're given, right? 1 1 1 1 2 2 1 1 2 2 1 1 1. But you can see that you could make it all white, all one, and then color 2 over it. All right, in this example, it's far more complicated, right? But you can make it all one, and then put the 3s here, and put the 4s here and the 5s here, and you'd get this resulting array. You look at this example, so let's just draw that out. So it's a 3 by 3. So we'll just make the grid first. All right, so we make this grid. All right, and then we'll say that color 1 is blue, so 1, 2, 1, 2, 1, 2, 1, 2, 1. And then we'll make red color 2, 2, 2, 2, 2. And then we'll just, I guess we could highlight over. So we have these blue cells, right? And we have these corresponding red cells. I'm apologizing that I'm wasting so much time on graphics, but there is studies that show that being more colorful and artistic in describing something can actually make it more comprehensive. Okay, so it's impossible to form the target grid because it's not allowed to print the same color in different terms. Right, yeah, like how would you make this system, right? Like you can only print red, then blue, or blue, then red. So if I printed blue, right, well, blue has to be a rectangle. So blue has to span this whole space in order to be drawn. So I'd have to draw blue. And then how am I going to draw red? Like red has to be a rectangle. And red also spans the whole space. So red would have to cover the whole space. Okay. So how do you do this problem? Well, let's look at these constraints first. Okay, so there's only 60 colors, right? Because target grid row column is less than or equal to 60, and each value of a cell is a color, and it's between 1 and 60, so it's only 60, so that's not bad, right? And this is only 60. So it's only 60 by 60 by 60 total possible things that could be a combination, right? Meaning like there's 60 by 60 spots, and there's 60 colors that could be in each spot. So a brute force would say, okay, there's definitely a solution if there's a solution to this problem. Well, let's not go there because I don't even know if that's true. Anyways, let's keep going. So what? So what's a key observation of this problem? Well, look at the constraints of how you have to draw this grid, right? Since you can only draw a color once, and it has to be a rectangular shape, for any color you see in a grid, like let's look at this system. So this is a pretty involved problem, right? So let's look at this graph here, this grid here, and that's a 4x4. Maybe I should edit my videos so you can like see me draw these faster. Give me more. If you subscribe to my channel, and if I get enough subscribers, then I'll be willing to put more production value into the videos. But if I don't have a bunch of subscribers, who gives a shit? Okay. 1 1 1 1 1 1 1 1 1. We'll make this 3 3 3 3. That's not even the right thing. I'm an idiot. This is 5 5, and we got a last color. Come on, there's gonna be a rainy color here. Blue, green, red. 4 4. All right, so we have 4 here. We got 4 here. We got blue here. We got yellow here, and we got a little green here. So how would you make this system? So what's an observation we can make from the system? Well, let's look at blue, right? Because blue is like the color that's covering the most. It kind of just determined in this problem, like, okay, given this ending state, right, we can build out this state because with ones everywhere. How do you know that ones have to be everywhere? Because you're just given this end state, right? You're just given this state here. How do you know that ones have to be everywhere in order to build this graph? Well, I guess the observation is, well, since you can only paint a color once, right? So 1 was only painted once. How are you going to create a rectangle where you have ones in the following spots, right? Ones have to be in this spot, and this spot, and this spot, right? Well, if I'm drawing a grid, right? So let's think about this grid again. And let's say, well, I need there to be ones. I need there to be ones here, 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 and here. So how do I draw a rectangle that fits that? Well, a rectangle needs to be this long, right? Now, it has to be a rectangle, so I can't, like, cut up like this. So the only way I'm going to get the elements down here is by making it this long here, right? And I can't do this, so the only way I'm going to get this last element on this side is by going down this far. And I have to get this element on this side. So the only way I can draw a rectangle that'll cover all these elements is by making this square rectangle, right? What about the blue? What about green? Well, for green, I have spots here, here, and here, right? So I have to go this far to get these two elements. And I have to go this far to get these two elements. And I can't, like, make a triangle, so it has to be a rectangle again. So the rectangle has to look like this. What about for yellow? Well, for yellow, it's a perfect rectangle, right? I only have, there's elements here and here. I can just cover that easily. And what about for 4? It's the same situation. It's a clear rectangle, red like that. Right? So since you're constrained by a rectangle shape, when you see the elements in the resulting array, you know exactly what rectangle had to be drawn to put the elements in those places, right? Like if I have a system, let's just do a generic system really quickly, right? And I have nodes here, 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 and here, right? I know that, okay, I got to go this far to get this one. I got to go this far down to get this one, this far down like this, right? So you always know the shape of the rectangle. And from like a very quantifiable way without looking at it, right? What's the quantifiable way to know the coordinates of the rectangle? Where you need to know the pivots of this system, right? Like how far left is it? Like for 1, right? Like what's the farthest left one is, right? And what's the farthest right one is? And what's the lowest or the highest value for 1 here? What's the lowest value for 1 here? Right? For green, how far left are the greens? How far right are the greens? How far down, up? And that'll give you the coordinates of the system, right? If you know the minimum place it is, the minimum row it is, the maximum row it is, the minimum column it is, the maximum column it is, that'll give you the rectangle that will have to be drawn to fit all of these points, right? Like the minimum row for 3 is 1, the maximum row for 3 is 2, the minimum column for 3 is 0, 1, 2, the maximum column for 3 is 0, 1, 2, 3, right? So you get those values, and that will tell you the corresponding rectangle you have to draw to fit the data, right? So when I look at this problem here, right, I can look at, for 5, I can say, okay, what's the minimum row for each color, the maximum row for each color, the minimum column for each color, and the maximum column for each color, right? And why did I make that blue? I have no idea. So if I run through this idea for each color, so let's do that for each color. So we'll do blue, green, red, yellow. Okay, so what's the minimum row? So we'll call this is the origin here, so 0, 0, and this is 0, 0 here, this spot, and then 0, 1, 2, 3. I don't know what I'm doing, right? 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3. Okay. So what's the minimum row for blue, right? Well, the minimum row for blue is here, right? That's the minimum row for blue. What's the maximum row for blue? Here, right, which is 3. What's the minimum column for blue? 0, which is here. And what's the maximum row for blue? 3, which is here, right? So the coordinates of this rectangle are this point, are from, so for the resulting rectangle we're going to draw, right? I'm just arbitrarily drawing a rectangle. I don't know its final shape, but this point of the rectangle is going to be min row, min column. This point will be min row, max column. This point is max row, min column. And this point is max row, max column. All right, and we can see that for this, right? This is 0, 0, 3 for min row, min column. 0, 0, 0, 0, 0, right? You can just mix and match, and you'll see that for blue, that's the corresponding figure. All right, for 3, what's the min row? The min row is 1. The max row is 2. The min column is 2. The max column is 3. What about for 4? The min row is 2. The max row is 3. Let's make these colors right. Min row is 2. Max row is 3. Min col is 3. And the max col is 3. All right, what about for 5, our last color? So min row is 3, max row is 3, min column is 0, max column is 1. Okay, so that's the system to get all the positions of where the rectangles need to be drawn. And I think that's pretty intuitive, because when we're looking at this problem, we have to know how something was printed in order to find out if it's a valid printout, right? And that's kind of how the example works, right? It tells you how the rectangles would have to be printed to get colors in the corresponding spots. And since we can only print a color once and it has to be rectangular shape, we know from the colors in each spot what had to be printed. So this is very intuitive in terms of this is an operation you probably need to do. Okay, so how do we then efficiently, in time complexity terms, find these min rows and max rows for an element? Well, what you can do when we're eyeballing it is look at each element individually, right? Like, so I look at this and I ask, like, okay, for this color, is this less than what I think is the min row? Is this less than what I think is the position of this color's row less than the min row? Is it greater than the max row? Is the position of this color's column, is it less than the min column? Is it greater than the max column? And I can do that for each grid element, each cell, look at the color at that cell and find if it is greater than what I think is the maximum, less than what I think is the minimum in terms of rows and columns. So let's go ahead and just do that first before we continue. So in order to do that, we'll create these 4 arrays. Now we know there's 60 colors, but we don't know what 60 colors are being used. So we'll just do a default dict. And for a min row, we'll assume that we'll just set the initial value to infinity, because that color will exist, but any position will be less than infinity. So then it always gets set to whatever the first time we see it is, right? This is the standard approach. So we'll say min row, max row. We'll assume that the max row is the opposite, which is negative infinity. Okay, my computer's getting hot. What did I just do? Okay. Assume that it's negative infinity. And then we'll do pretty much the same thing for min call, max call. Same idea. All right. So what we do is we look at each grid cell. So we look at ij we'll do product, because we like to show that we know really obscure. This is basically just a one-line. This is a one-line nested for loop. Okay. Don't get threatened. Don't feel threatened by it. Just a weird quirk of me doing Leetcode for so long. I know some strange ways of doing things you know how to do in different ways. Okay. So this is just a nested for loop. So this will just look at each ij pair of this matrix. All right. Then we'll say, well, the value, the color, right, is target grid at ij. Sorry, I've been working with NumPy this weekend. ij, and then what will we do? So then, blah, 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 blah. Basically, the min row is now for this color. And we'll do the max row too of this color. is, well, is this less than what I think is the min row of this color already, right? If I counter this color again, I'm like, okay, is this less than what I think it is? Right, I already have a value for what I think the min row is for a color. But if I see it again and it's in a position that's less than what I think is the min row, well, then this is the actual min row, right? And I, J, those are the positions within the system, so that will tell you where something's supposed to be. Max row, min row, we'll go here. Max row, and then we play the same game. We play the same game for the columns, right? So this is the min call, max call, but instead of looking at I, we look at the jth position of the element, of the color in the cell. And you know that I love making things shorter. I could actually make this one line, but let's not do that because that would be an insanely long line and it's already long enough. Okay, we can make all this one line, right? We can make all of what I've just done. This could be one line, and this could be one line. So it'd be 2 lines. We can make this a 2-line solution. And maybe I'll say that it's 2 lines in the end, just for fun, just so you guys can see how ridiculous it is when you're in Python and trying to claim that your solution's better because it's shorter. I can make this solution so short you couldn't even read it. Very long 1 lines. Okay, so what's next? So let's then look at each color, and we can just do min row because min row will be populated with each color that exists, right? Because you're always filling. You could use any of these, but these basically, each key inside of these default dicts is a color that you've encountered. So if we just look at all of these colors in min row, we'll know all the colors that we've encountered in the whole system. We could just print the color, the min row of the color, the max row of the color. So I was just looking at my tablet to make sure this is the same. The min call of the color and the max call of the color. So let's do that really quick. It's going to say it's wrong, of course, because we haven't returned anything. We haven't finished this problem yet. Yep, I forgot to do that over here. So now this is getting even longer. Great. Max call, min call. What's the problem? Name call is not defined. Oh. Alright. Alright, so dude, I am so sorry. Making a lot of mistakes over here. Min call equals min call. Max call equals max call. See, I don't like this negative infinity thing. That seems weird. Color. So we got min row, max row. Oh, because this is supposed to be the max, right? Because we're getting bigger. Right, so the max row is the max of what I think is the max row in I that I've encountered. Okay, so finally got that working. That's why it's really good to debug before you continue, right? So this is just a good lesson when you're in programming interview. Ask if you can kind of try to break it up into components, right? If you can see the components of the problem, break it up into components and then solve each of those components and then integrate them in together at the end. Right? Don't try to rush it and do everything at once unless they don't allow you to kind of debug as you go. Because it's just gonna make the problem harder, right? So we have color. So this is not this problem. So this is a different case. So let's change it, our test case, to example 2, which we've been working on because it's a little more complicated. So it kind of gives us an indication of how this problem works. And then let's compare it to kind of what we hand drew out and see if those things match. So For color 1, we have 0, 3, 0, 3, 0, 3, 0, 3. For color 3, we have 1, 2, 2, 3, 1, 2, 2, 3. For color 4, we have 4, 2, 3, 3, 3, 2, 3, 3, 3. For color 5, we have 3, 3, 0, 1, 3, 3, 0, 1. Okay, so this is convincing enough for me, right, that this process works, right, because it kind of makes sense. It'd probably work for anything else. So I'm allowing myself to believe that this code is correct just given this one test case. And in an interview, you're probably going to have to do that too because you don't have a lot of time. But if you can kind of prove it to yourself, like in a short problem, like, okay, this probably works, so let's move on. Okay, so now what do we have to think about? Well, when we look at this system here, so let's erase a lot of this junk. It's not junk, but it has served its purpose. Don't take everything with you, please. Okay, cool. Okay, so when we're looking at this system here, in order to print 1, you can kind of think of this as like a prerequisite course class kind of pair. In order for this system to work, right, 4 has to cover 1, right? Because remember, the system started out, right? The system started out with all 1s. So since the system started out with all 1s, 4 has to cover 1. Right? 4 has to be on top of 1. 4 has to replace 1. 4 has to come after 1. So in order for me to print 4, I have to print 1. Right? In order for me to put 4 on top of 1, 1 has to be before 4, in a sense. Right? So anywhere I look, a color has to cover another color. And you can tell that it has to cover that corresponding color because you know the positions of where all of the rectangles have to be drawn. Right? So you know which color is being covered up by a subsequent color, right? Because since I know that this is green, I know that 4 has to cover 3 as well. Right? I know that 4 has to cover 3 because 4 is in the box where green is going to be colored at some point, right? Because we have to draw that rectangle. And so let's draw these rectangles again. I'm sorry that I erased it on the other case, but I think this will give us some good intuition onto how this problem works. Right? So in order for yellow to be drawn, or color 5, let's erase this. In order for me to color 5, well, that also has to be done because that's going to cover up, right? 5 is going to cover 1. What about 3? Well, 3 is inside of the rectangle of 1, so 3 also has to go before 1. Okay? So what this system really reduces to is a graph, and we have to look at each node and determine if it can be traversed in this manner. Now, what I mean by that is, do I have a system where I can draw rectangles and the rectangles that exist within them can be drawn subsequently? Right? So if we look at a problem that doesn't work like this, right? In this problem, what would it mean in order for something to go wrong? Why doesn't this work? Well, for this problem, we have blue and red rectangles, or let's do something slightly different. Let's do the gun example, because I think that'll be a little bit more intuitive, because that is more of an edge case. Okay. And then 2. Wait. What the hell am I doing? All right, this is 1, this is 1. Okay, so what's the rectangle for blue? Well, blue rectangle is the whole thing, and red's rectangle is this. Okay? But then inside of blue's rectangle, inside of red rectangle is another blue rectangle. Here. Right? So in this system, inside of each rectangle, right? So I guess the idea is if you look inside of a rectangle, you look at the colors inside, and you know, okay, since I drew this rectangle and there's another color inside of this rectangle, that other color inside of a rectangle needs to be drawn after, right? So when I look at blue's rectangle here in this problem, so this is how you would build a graph. You say, what rectangles are inside of my rectangle that would need to be drawn subsequently? Okay, well, I have 3. Right, so for 1, we have a 3 rectangle inside, we have a 4 rectangle inside, and we have a 5 rectangle inside. Then I look at the 3 rectangle and I say, okay, which thing's inside of here? Well, 4 is peeking in, right? So there's a 4 rectangle inside that needs to be printed. And then I look at 4. Notice in 4 there's no rectangle encapsulated inside of it, right? There's a rectangle that shares a portion, but it's not inside, right? Because it's actually inside of somebody else's rectangle, but it's all red. It's all rectangle. Red's rectangle is all itself. There's no other color inside of its rectangle. That's the point I'm trying to get at. And same with this yellow rectangle, right? It's all yellow. There's no other colors rectangle which is inside this rectangle. So this is the resulting DAG, right? And it's the same system here, just showing you exactly how you would kind of find that. So when you look at blue, you say, okay, what colors are inside this blue rectangle? Well, red, right? So red points inside. But then you look at this red rectangle and you say, okay, hey, red rectangle, what colors are inside of your rectangle? Well, blue. So that must mean also that blue comes in here. So why doesn't this work? Well, there's no way that you can draw this, right? Because in order to draw blue, you have to draw red. But in order to draw red, you have to draw blue. So you have a cycle. So if there's any cycle in the system, there's a case where you can't make everything happen, because in order to make A happen, you have to make B happen. In order to make B happen, you have to make C happen. And in order to make C happen, at some point, you're going to have to make A happen again. So you can never meet the constraints because you're stuck in a cycle, right? This system works because there's a clear directed acyclic graph where you can see exactly what needs to be printed before subsequent items, right? So I know that I can make this work because I can print blue, and then I can print yellow, and then I can print red, and I can print 5. Or another way I can think of this is saying, well, how do I get this system back to 0? I can remove 5. I can remove 4, make those zeros out. I can 0 this system out, and then I can 0 this whole system out. So if I look at each rectangle and I look at the colors inside of them, from that color to the rectangle color that's corresponding, I create a link, right? I create these links in the system. Then I can make the problem work. So let's go ahead and do that. So we look at each color, right? And then we'll look at the rectangle that has to be drawn to draw that color, right? Which is just what? So we'll look at ij pairs and product again. Again, this is just a for loop. And what's the range of the rectangle? Well, the rectangle goes from the min row of the color to the max row of the color plus 1, right? Because we want to include the last element. So that's the row range. Now what's the column range, where we have the min call of the color all the way to the max call of the color plus 1. All right, so that'll give you the ij range. It's just an S of 4 loop again product for each grid cell, for a color, right? So what do? We look at it and we say, well, let's create a graph. So a graph for the colors, there'll be a default dict, lambda, not lambda, a list. Yeah, that should be fine. So if it's its own color, right, in this system, notice when we looked at our own color, we don't add that color to our system, right? Only if we look at a color that isn't the color that we're supposed to be looking at, right? Because we're trying to find different colors that exist within a colors drawn rectangle. So only if, right, if target grid at ij doesn't equal the current color, then we have to add to our graph at target grid ij append color, right? And that's what we did here, right? Notice, can I just undo a lot of this stuff, because it would look nice at one point and then I just played a weird game. Okay, so when we look at this grid, right, notice when we have blue here, right, when we saw color inside of blue's grid, we added an edge from the color inside of blue's grid to blue, right? Same with green, right? When we looked at green's corresponding rectangle, when we saw color inside of green's rectangle that wasn't green, we added an edge from that color that was inside of green's rectangle to green. All right. So if the grid color isn't the one that we're supposed to see, we say the one inside of the rectangle color, add this color. Okay. So we do that, and then how do we? Well, remember, it just really gets down to trying to find a cycle. So let's just run DFS. So we'll say color equals default dict. And I'm just going to do basic topological sort to show you how to find a cycle in a graph. And I'll just run through that code really quickly. I'm imagining if you're doing a hard problem like this, you probably know how topological sort works. So we'll do, now I've been perfecting my approach to topological sort. So there's probably going to be some things where you're like, oh, I've never seen someone do it like that. Okay, and then C of U equals 1, and then when you're done, C of U equals 2. C of U equals 1 means that it's on the stack. C of U equals 2 means that it's finished being traversed. If that doesn't make sense, then probably spend some time reviewing other videos about topological sort. Right, that is a fundamental algorithm you need to understand in order to approach graph problems. Okay, and then we'll look at each neighbor in G of U, and we'll say if not, I don't want to make this longer than it needs to be, but let's just do it like that. Okay.
Are you done?
No, I'm not doing. If not any, okay, if any of DFS, the neighbors, is false, for V in G of U, we return false. Otherwise, if it gets to the end, we return true. And then what do we have to do at the end? Well, we just return that everything works. So there's no cycles for any node. So we say all DFS of U for U in, we can just do min row again. All right, so this is just a standard way of finding a cycle. I kind of got a little artsy here. All right, of course there's going to be an issue because I just wrote a lot of code. All right, let's run that. All right, let's submit it. And there you go. That's the solution to this problem. So what is the runtime? What is the space time? Let's see. So it's weird that it did that. Okay. So for each color, we're going to need a max row and a min row and a max call. So that's 4 times C, where C is the color. All right. We're going to do DFS on each of the color. We're going to build a graph on each of the color. All right, so it already uses MN space, right, for target grid. But we only need to use an additional C space for each of the colors. Right, but what about the graph? No, because you would only add it for each color. Huh. Well, it's I'm not exactly sure, because if you had a graph, and I don't want to spend too much time going through runtime because it's boring, but or space time, because if you had a graph, you had a color. At most, colors minus 1 can be in that system, right? You'd have to have neighbors for each color minus 1. So it's definitely at most C squared. Because if I had a color like this, and I had to make a graph for all the colors that were inside, right? Maybe each subsequent color, right? A blue looked like this. Then blue's graph would have to be like this. So there'd have to be a reference from here and here to C. Right? The idea is each graph might have to have each other color as a neighbor. I'm trying to think if that could happen. But even if it can't get worse than that. So there's at worst. Let's do it here. So in terms of space, let's do it at the top actually. So in terms of space, it's at worst O of C squared, because each color could have each other color inside of it. So you'd have to add references to each of them. Right, that would give you C squared references. In terms of time, well, this, we just look at each grid element. So that's M times N times, right? Because there's M rows and columns. This, though, this could be at worst O of M times N times C, right? Where M is the number of rows, N is the number of columns, and C is the number of colors. Because you could have a case, right? In the worst case, and I just thought about this, if you had a grid like this, say it's a 4x4, imagine each color is like this somehow. How would that happen? That you had color, color, then you had color, 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 you had color, 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 right? For each of the colors. Color, color, color. I don't know. But essentially, you could have each color being inside, represent almost the entire grid, or approximately that. I don't know exactly the corresponding equation. But you could have the case where this looks at, you know, this looks at each color, and then you end up having a square that's the size of the entire grid. So you have to look at each color, and then for each color, you have to look at the entire grid. So that's time complexity M times N times C. All right, so that's it for that. Now let's see if I can make this any shorter. Okay, because I was kind of curious if I could do that. This I'm not going to change. Just trying to show you guys that you can make crazy one-line solutions just for fun. You can probably exit out of this video if you know how to do it now and you don't care, but sometimes I like to do that just to show you how ridiculous Python can be. And then you could be like, I have a one-line solution, actually. All right. I had to focus here because this can get crazy. actually means that this can go. Oh no, I shouldn't have to say G equals this. This can also go on another line. Just one really long line of establishing all your variables. This I can't really change because I have to set CU to 1 and then CU to 2 after I do all this. This I can also make one line by doing what? I can do a filter lambda u, and you say target grid u0 u1 not equal color, and then I have no idea but now I don't know where this goes. See, this is why this is problematic. Okay, so you have that u lambda u. Have I officially made this so short that I can't even read it? See, that's the problem. I told you this would happen. Okay, this doesn't go there. Okay, so that's range of this. We have range of this. We have a product here. And that's going to create... Why is it mad about that, though? You don't have a terminator, so why are you mad? We got our lambda function here as the key. Lambda u, target grid, u0. Oh, shoot. Product. So range. Filter. Now that's one line too. And then there you go. So this would be the... what I call this. If I really want to just show people how ridiculously genius I am. All right, somebody just turned on my car, so I'm gonna call it here. But it's a what, 11 line solution. All right, everybody. See